Okay, it's my pleasure to welcome Paul Schwahn of the University of Stuttgart, speaking on the Lichnerowicz Laplacian on normal homogeneous spaces.
Thank you, Karen, for the introduction, and also thanks for the invitation. It's a pleasure to be here. So, yeah, the Lichnerowicz Laplacian is a curious differential operator, and yeah, let's see what we have here. Okay, so first, let me introduce you to what the Lichnerowicz Laplacian is and why it's an interesting operator. I'm going to talk about the stability of Einstein metrics, because this is basically the main point or one of the main points that motivates studying the Lichnerowicz Laplacian. And yeah, I'm going to look at it on homogeneous spaces. So the easiest or the most well-behaved homogeneous spaces are symmetric spaces. So we're first going to take a look what happens there, and then looking at the slight generalization of it are the normal homogeneous spaces, for which I found some interesting results regarding the stability of Einstein metrics, and I'm going to demonstrate some of them at the end. Okay, so the Lichnerowicz Laplacian, how is it motivated? So on differential forms, so alternating tensors, we have this Weizenberg formula for the Hodge-de Rham Laplacian. Namely, we can write this as nabla star nabla, where nabla is the Lebesgue-Witten connection. So this nabla star nabla is the rough Laplacian or Bochner Laplacian, plus some fiber-wise curvature operator Q of R. And this Q of R is called the standard curvature term sometimes. Yeah, this is right. It can be defined in several ways. This is one of them when you write it down. So this curly R is it's called the curvature operator of the first kind, and it's basically you get it from the Riemannian curvature tensor by understanding it as a symmetric endomorphism on bivectors. So you plug in a two form and or a bivector, and you get out a two form. Yeah, and then this correspondence here between bivectors and skew-symmetric endomorphisms is via the metric itself. It's kind of a technicality, but I think this is a good way to introduce this Q of R term. We're going to use this later. Okay. Yeah, this is kind of a natural thing, not natural endomorphism. On the tangent bundle, if we apply it there, then it just is the same as the Ricci endomorphism. So you take the Ricci tensor and you raise one index via the metric. So you put a vector in and it spits out a vector. On two forms, we can write this Q of R in terms of the curvature operator itself, namely it's 2 times R minus this. Okay, the second part here means that we take this Ricci endomorphism and extend it to tensors, to higher tensors as a derivation. Okay, on symmetric two tensors, we can do something similar. We have this R circle. This is also an operator on symmetric two tensors that you get from the Riemannian curvature. It's also sometimes called the curvature operator of the second kind. And we have this formula. Sometimes the sign conventions are a bit differing. Okay, so the striking fact is that this rough Laplacian and this Q of R can be defined on any tensor bundle, so not only on alternating tensors, not only on differential forms. And with tensor bundle, I mean this is some vector bundle that's associated to the frame bundle of the manifold via SON. So we can take this Weizenberg form, this right-hand side of this Weizenberg formula, we can take this as a definition of a differential operator, and this is called the Lichnerowicz Laplacian. So this is the general definition of it. Okay, what's cool about the Lichnerowicz Laplacian is that it's a natural operator. It commutes with all parallel bundle morphisms, and it also commutes with certain differential operators, for example, this divergence operator. So this curly S means this is our symmetric 2 tensor fields. These are symmetric 1 tensor fields, or just 1 forms. So this divergence takes a 2 tensor and maps it to 1 form. Okay, yeah, the main setting of interest are the tt-tensors. Tt stands for divergence-free and trace-free. So these are symmetric 2 tensors that are in the kernel of the divergence operator and in the kernel of the trace, so contraction with the metric. And yeah, since this Lichnerowicz Laplacian commutes with the divergence and with the trace, it preserves this space of tt-tensors. Okay, and why do we want to look at this specifically? And now here comes the reason, because this features in the stability analysis of Einstein metrics. Okay, so let me tell you a bit about this. Take any compact manifold, orientable, then we can take a Riemannian metric and associate to it its total scalar curvature. So we take the scalar curvature, it's a function times the volume form and integrate it over the manifold. This is called the Einstein-Hilbert action. It was studied by Einstein and Hilbert back in the days. And if we take it's called action because by the principle of stationary action, we get as Euler-Lagrange equations precisely the Einstein equations. So in mathematical terms, it means that the critical points of this functional, if we do this volume normalization restriction, so we restrict to volume 1 metrics, the critical points of this function are precisely the Einstein metrics. So this is Einstein metrics. As a reminder, this is metrics such that the Ricci tensor is a scalar multiple of the metric. So these are the Einstein field equations here with a cosmological constant, namely this E. And yeah, so this is basically the variational approach to general relativity as was it developed by Hilbert. Okay, but here we are on a Riemannian manifold, not on a Lorentz manifold, so we only care about Riemannian Einstein metrics for now. Okay, so if we have such a critical point, then we can ask what the type of this critical point is. Is it maybe a maximum or a local minimum or a saddle point or whatever? And in fact, we can answer that question if we consider the second variation. So the first variation at some Einstein metric is 0 because it's a critical point. The second variation is the next term in the Taylor expansion, basically. And if we suppose that our manifold is not isometric to a round sphere, then we can do something nice. We can decompose the formal tangent space to this M1. So recall from the last slide, M1 was the set of Riemannian metrics on M, which have unit volume. So this is, in a sense, this is an infinite dimensional manifold. We can take a formal tangent space of this at G. G should be an Einstein metric. I forgot to write that here. And it decomposes into 3 parts. The first part is this, we just take the metric and we multiply it by some function. So this is the part that's tangent to conformal change. And because we want to preserve volume, these functions have to be orthogonal to constants. So they average out to 0. The second part is the set of Lie derivatives of G. So this comes from changing the metric by diffeomorphisms. If we take a metric and a smooth family of diffeomorphisms and take the pullback, then they will have the same scalar curvature. So this S functional will not be changed. And this space of Lie derivatives is tangent to this diffeomorphism orbit. And the third part is the space of tt-tensors. And this is the interesting part. So this splitting is orthogonal with respect to our Hessian, or with our second variation. So we can study it separately on each of these 3 summons. And the first one, it's always strictly positive. So we always know that an Einstein metric locally minimizes its total scalar curvature in its conformal class. Yeah, as I explained, the scalar curvature and also total scalar curvature is not changed under diffeomorphism. So of course we expect this second variation to just vanish identically on the second summand, so on these Lie derivatives. And on the third summand, it's almost negative in the sense that there might be a finite dimensional space where it is positive or 0. And this is the interesting part. So this is the space of tt-tensors. And on this space, we can write down the second variation in a very nice way. And this is where the Lichnerowicz Laplacian appears. So it's this L2 product of the Lichnerowicz Laplacian and then minus 2 times the Einstein constant. And then, yeah, you see, so this co-index and nullity of the second variation of the Einstein-Hilbert functional are directly related to the spectrum of our Lichnerowicz Laplacian. Okay, so we want to, yeah, so what does stability mean now? Stability now means that this is in fact negative. So this, or equivalently, that the Lichnerowicz Laplacian is greater than 2e. So we can talk about this upper and lower bounds because the Lichnerowicz Laplacian is a self-adjoint operator. So this means that so this implies that the metric is a local maximum of the Einstein-Hilbert action if we restrict it to the class of metrics with unit volume and constant scalar curvature. Just as a fun side note. Okay, so this is stability. We can do it. Yeah, we can weaken this to semi-stability if we just want it to be greater or equal than 2e. And of course, there's instability. So there might, if there's a destabilizing direction, this would be this h, such that if we plug it into the second variation, it is positive. And yeah, this translates to there being some eigenvalue of the Lichnerowicz Laplacian on tt-tensors that's smaller than 2 times e. Yeah, okay, this is all what I already mentioned. So if the metric is stable, then it's also a local maximum of S among constant scalar curvature metrics of the same volume. And if we are only interested in the null directions, so the ones which are annihilated by this second variation, or which are precisely eigentensors to this 2 times e, these are the ones that infinitesimally preserve the Einstein property. So they are called infinitesimal Einstein deformations. And they are interesting to look at because the moduli space of Einstein metrics is, as of today, still not very well understood. So, for example, if we pick an Einstein metric, we can ask, are there any other Einstein metrics closely nearby in some sense? And yeah, if there are no infinitesimal Einstein deformations, then we can answer that question with no. So this is one reason to look for them. Okay, so this is what the stability question boils down to. We want to analyze this spectrum of the Lichnerowicz Laplacian. Does it satisfy this estimate or not? Okay, some examples. So the round sphere is stable. We can, and the flat torus is semi-stable. We can just explicitly calculate this Lichnerowicz Laplacian there. This is not very interesting. An example of a unstable metric, if we have a product of Einstein manifolds with the same Einstein constant, then this product metric will again be Einstein. And if the scalar curvature is positive, then we get an unstable direction by doing this construction. We take this just so we take the one metric and the other metric, flip the sign of one, and then scale them accordingly. So then we get a tt-tensor, which is in the kernel of the Lichnerowicz Laplacian. And if the scalar curvature is positive, then this means this metric is unstable, because 0 is then smaller than 2 times e. A slight generalization of this is we can look at any Einstein metric on a total space of a Riemannian submersion, M, so B is the base and F is the fiber. And we can do the following. We can take the part of the fiber and scale it slightly with some parameter T. And it turns out that so we get a curve of metrics, or one parameter family of metrics, and it turns out that the tangent to it is a tt-tensor, and this might sometimes be an instability. This depends on a simple to check condition for the scalar curvatures of B and F. And also sometimes this construction is interesting because it might produce a second Einstein metric on the space. For example, the first non-round Einstein metrics on spheres was constructed by Jensen on these S4m+3, these fiber over quaternionic projective space with fiber S3. And if we scale the fiber of the round metric accordingly, we get a second Einstein metric. These are the squashed Jensen spheres. Yeah, there are many other results on instability mainly. So for example, in some special holonomy or weak special holonomy situations, it's possible sometimes to produce unstable directions from harmonic forms, from harmonic 2 forms or 3 forms or something. So there is, in this case, a topological reason. So usually if there are unstable directions, they have some geometric meaning. So this is what it boils down to. Yeah, and in the 80s, Norihito Koiso looked at symmetric spaces. For non-compact symmetric spaces, there is a curvature condition that actually shows stability in a pretty straightforward way. But for compact symmetric spaces, or particularly for those of compact type, so where G is compact semi-simple, there is this astonishing result that the Lichnerowicz Laplacian can be written as a Casimir operator. I will shortly explain what that is and what that means. And this enabled Koiso to analyze systematically the stability of these compact symmetric spaces. Okay, so yeah, let's now enter the homogeneous setting. We have some homogeneous space, G mod H. We assume G to be compact and also connected. And we look at a homogeneous vector bundle. So these always have this form. It's a vector bundle over M with fiber V, where V is some H module. And if we assume it to be complex, then that makes things slightly easier, but it doesn't need to be complex strictly. So assume we have such an homogeneous vector bundle. The space of smooth sections can then be identified with just the space of smooth functions from G to V, which are equivariant under H. So if we, so the right multiplication with some element in H pushes through this function and turns into action on V. And on this space of functions, the group G acts by left translation. And this is called the left regular representation. So it's an infinite dimensional representation of the group. And the natural thing to ask is, can we write this infinite dimensional representation as a sum of finite dimensional modules? And the answer is essentially yes, we can. By the Peter-Weil theorem, we can, so this is the closure of a direct sum. So as a G module, this decomposes into the sum of these spaces. Okay, what are the V gamma? V gamma is a way to enumerate the finite dimensional irreducible complex G modules. So there are countably many of them if G is compact. And this other thing is just, so the G does not act on this Hom space. The G acts only on this V gamma. This Hom space is a finite dimensional vector space that does the job of counting the multiplicity of V gamma in our left regular representation. And the cool thing is that the dimension of this Hom space can be calculated very easily using representation theory. Okay, so now if we have such a homogeneous vector bundle, we know what the functions do. So this is, in a sense, a Fourier series. We can look at some invariant differential operator or pseudo differential operator on the space. And by Schur's lemma, it will only act. So this is an invariant operator that maps this decomposition here to itself. So by Schur's lemma, it will basically leave these V gamma untouched and will only act on this Hom space as some linear map for each distinct gamma. So the gammas are, well, okay, right here they are just, this G hat is just an index set, but we can think of gamma as highest weights and this V gamma as highest weight modules. Okay, so we start with some invariant differential operator and we get a sequence of linear maps. And now the question is, we want to apply this ultimately to the Lichnerowicz Laplacian. The question is, what are these linear maps in our case? So we take symmetric tt-tensors. We can also just take them to be traceless, which is indicated by this index 0 here. And yeah, let's find out what happens here. Now in the symmetric case, this is actually pretty easy. In hindsight, it's easy. I think back then it was hard to find out. But yeah, we have these Casimir operators in representation theory. So let me remind you what that is. For some compact Lie group, and where the Lie algebra is equipped with some invariant inner product Q, we can define a Casimir element. So this is an element in the universal enveloping algebra of the Lie algebra G. It can be written like this. There's also some other way if the basis is not orthonormal, but it's not important right now. What's cool is that this Casimir element lies in the center of this universal enveloping algebra. And if we apply the push forward of some representation to this Casimir element, then we get some equivariant endomorphism of V, where V is our representation space. And this is called the Casimir operator. Okay, so this just introduces the notation for the Casimir operator. But the cool thing is that this Casimir operator, if the representation V is irreducible, then by the lemma of Schur, this Casimir operator must just be multiplication by some constant. And what this constant is can actually be computed pretty easily by this formula of Freudenthal. So if we interpret gamma as a highest weight, so for that we have to do some choices. I will just read those under the rug. So we have to choose a maximal torus, we have to choose a set of simple weights and simple roots, and so on and so forth. And if we have done that, then we can view gamma as sitting in some vector space, this dual of the torus Lie algebra, and we can take it in this inner product here. And this delta G, this comes, which comes in at this point, is this Weil element. So we can define it as a half sum of positive roots or sum of fundamental weights of G. Okay, so this formula is, it's straightforward to evaluate once you have your weight lattice and once you have your inner product. Yeah, okay, so now let's return to our homogeneous vector bundle. In this case, let's say it is a tensor bundle. And if the space is symmetric, this is a crucial assumption, then it turns out that, in fact, this Lichnerowicz Laplacian coincides with the Casimir operator on the left regular representation. So take a moment to marvel at this. We have this Casimir operator, which is a well-understood object in representation theory. And on the other hand, we have this Lichnerowicz Laplacian, which is a bit mysterious, but also it's a natural object to study. And it turns out on symmetric spaces, they are the same, or one is an instance of the other, which is pretty cool. And also, as a side note, this curvature endomorphism can itself also be expressed as a Casimir operator, namely as Casimir operator of the smaller group, H. And since the functions that we apply to are equivariant, we can push this entire thing through to a Casimir operator acting just on the fiber. And the fiber is V. And this makes sense because this Q of R is not a differential operator. I mean, it has order 0, so it's just a fiber-wise term. Okay, so this means that if we translate this Lichnerowicz Laplacian in the Fourier image, so we fix a highest weight gamma, and we want to know what this linear map associated to the Lichnerowicz Laplacian is. This is just a multiple of the identity, namely this multiple here, given by Freudenthal's formula. So basically, the spectrum of the Lichnerowicz Laplacian is no mystery anymore. We know what the possible eigenvalues can be. And it only remains to find the multiplicities of these eigenvalues, and this can be done using representation theory. There's a slight issue regarding the divergence, because we have only talked about traceless tensors here, but I will come to that in a moment. Yeah, so the upshot is, on a tensor bundle over a compact geometric space, we can easily compute the spectrum of this Lichnerowicz Laplacian, and this opens the door for the stability analysis of compact symmetric spaces. So the results of Koiso look like this. So Koiso, back in the 80s, did the bulk of the work. So he considered irreducible symmetric spaces of compact type, and basically it turns out, bullet point 3, most of them are stable, and the ones which are not stable are listed here. So we have bullet point 1, the ones which have infinitesimal deformations. So these are so they have eigentensors to this critical eigenvalue 2e. And bullet point 2, we have these list of spaces which are unstable. So they have subcritical eigenvalues. So eigenvalues smaller than 2e. Okay, so yeah, why are there several authors here? Well, Koiso did most of this, but he left some gaps. And these gaps were only recently filled by myself and Uwe Semmelmann and Gregor Weingart in 2 articles. And the gaps were left because of this divergence issue. So there were sometimes candidates for destabilizing directions, but it was not clear whether they are actually divergence free. And in fact, yeah, so this all works out pretty well on this bundle of traceless symmetric 2 tensors. But what about tt-tensors? And this can be remedied like this. So we have a short exact sequence, and here, curiously, we have the killing fields appearing, the space of killing fields. And from this, the sequence is nice because every arrow here in the homogeneous case is G invariant and also commutes with the Lichnerowicz Laplacian. So it descends to a sequence on the eigenspaces of the Lichnerowicz Laplacian. So what we obtain is a dimension formula. So if we want to know how many tt eigentensors there are to some eigenvalue lambda, then we just have to compute its multiplicity on traceless symmetric 2 tensors in 1 forms. And in one case, this comes from the killing fields, we have to add the dimension of G. So the killing fields are the infinitesimal generators of isometries, and in the symmetric space of compact type, the isometry group is just G. So we just add this dimension of G if we are at the critical eigenvalue. Okay, and with this, finally, we could get the results that I just showed. So here they are again. Okay, cool. But that's, I mean, some time has passed since then. And the question is, what happens if we are not on a symmetric space? Then this equality fails. And this is where things get interesting, I think. So if we are not on a symmetric space, then yeah, the hope is that this Casimir operator can be reinterpreted as some other differential operator of significance. And the second hope is that we can find some nice expression for the Lichnerowicz Laplacian that's amenable to computation. And it would be especially nice if it was also in terms of Casimir operators, because we know how to find the spectrum of these by Freudenthal's formula. And as it turns out, this works out if we assume the metric to come from such an invariant inner product on the Lie algebra G. We need such an invariant inner product in order to find our Casimir elements. So somewhere this should play a role, and if the metric comes from such a product, then yeah, things work out. Okay, let me show you how this is done. So we take some homogeneous space, we take the group G to be compact and connected, and suppose we have this reductive decomposition. Reductive decomposition just means that this decomposition is invariant under the adjoint action of the group H. So if we apply, so or equivalently, the commutator of H and M lies inside M. So this M here can be thought of the tangent space of our manifold at the base point, or at some point. Yeah, there's this well-known correspondence. The G invariant metrics on M correspond to H invariant inner products on this tangent space. And we want something stronger. We want a normal metric. A normal metric means precisely what I talked about in the slide before that. The metric is supposed to be the restriction of some at G invariant inner product on the Lie algebra G. So in particular for such a invariant inner product to exist at all on the Lie algebra G has to be compact. Okay, so we introduce one further thing, namely this auxiliary tensor. We do it like this at the base point. So we take some vectors x and y in M. We take the commutator and then project this down to M. So this commutator so this is the commutator in G. So it lies in H plus M, and then we project it to the second component. And a priori, this is some invariant tensor field. So it eats two vectors and spits one out. And in fact, the vanishing of A is precisely equivalent to G mod H being a symmetric space. So this is just the third Cartan relation. So this tensor measures in some sense how far M is from being a symmetric space. If M is normal, so if the metric is comes from such an invariant inner product, then M is also naturally reductive. And this, by definition, means that this A tensor here is totally skew symmetric. So we can think of it as a 3-form. Okay. Yeah. Okay. Recall our first goal. We want to reinterpret this Casimir operator as some differential operator. Okay, so we need another connection to make sense of this Casimir operator, and this canonical connection or Ambrose-Singer connection comes to our rescue. So on any reductive homogeneous space, reductive just means that we have such a reductive decomposition. We can define this connection. I'm not going to, there's several equivalent ways to do it. I'm not going to define it explicitly. I'm just going to list a few nice properties that this connection has. So first of all, it comes from a principal connection on this H principal bundle G over G mod H. Second, it is an Ehresmann connection. So we can think of it being defined in terms of a horizontal bundle inside the tangent bundle of G. And this horizontal bundle is just the one that's consisting of all the left translates of our reductive complement M. Yeah, we can describe it in terms of the Nomitsu map. So this formalism is explained, for example, in this book of Kobayashi and Nomitsu. And this connection, so this Nomitsu map is basically parametrizes all invariant connection on such a homogeneous space. And this nabla bar is the one corresponding to lambda m equals 0. A very important property is that every G invariant tensor on M is parallel under this nabla bar. And also that if we take the covariant derivative with respect to nabla bar, then this corresponds to the directional derivative in this function space here, in the space of equivariant functions from G to V. And here we think of X in M as a left invariant vector field. Okay, so and this is actually the property that's going to be used later to actually compute stuff with this. Yeah, so finally, this is a metric connection because the metric is invariant, so it's parallel. And the torsion is precisely minus A. The curvature is given by this, so it can also be nicely or neatly expressed by these commutators and the projection to H in the middle. Okay. So now the cool thing is that actually if we are on a normal homogeneous space, we can relate the Levi-Civita connection and this Ambrose-Singer connection very easily. This is this Ambrose-Singer connection is a metric connection with skew torsion, and thus we can relate it to the Levi-Civita connection like so. So the difference between those connections is this tensor here, 1/2 times A. So pretty neat. And we define a new differential operator called the standard Laplacian. So actually this standard Laplacian is a construction that we can do for any metric connection with skew torsion on any space. And it's always always defined like this. So it's supposed to mimic the Lichnerowicz Laplacian. We take this rough Laplacian here plus Q of R bar, where R bar is the curvature of our Ambrose-Singer connection. And the cool thing is that analogously to the symmetric setting, this is now equal to this Casimir operator on the left regular representation. So this standard Laplacian, even though it may seem a bit strange at first, is very well understood because we can compute its spectrum as has been done before in symmetric spaces. Okay, actually, let me show you how to find this formula because it's actually not so difficult to prove. So the rough Laplacian, this is the easiest part. We can write it like so, like the sum over nabla bar EI squared. And then using this property that this nabla bar translates into the directional derivative, we can just write it as the push forward of the left regular representation of EI squared. And this is just, since E is an orthonormal basis of M, this is just the difference of these G and H Casimirs. We can extend this EI to an orthonormal basis of G and then subtract the H part again, so we get this difference here. Okay, now the question is what happens to Q of R, and this is pretty cool. If we have some tensor bundle means that V is some tensor power or contained in some tensor power of our reductive complement M. Or equivalently, this representation of H on V factors through this SOM. And then we can do something very neat, taking the adjoint representation of H on M. We can write our curvature operator of nabla bar simply as minus at composed with at adjoint. So we can make this computation in the universal enveloping algebra. So we take our Casimir element of H, so this lives in the universal enveloping algebra of H, and apply this add. So we have to extend this add, of course, to the universal enveloping algebra. So it extends to an algebra homomorphism. It pushes through the multiplication here, and then by a change of basis, or this is just linear algebra here, the last step. We can write this in terms of a orthonormal basis of SOM, and this is where this curvature operator appears. So we have shown, if we now apply this last arrow here, this last arrow from SOM to GLV, we see that Q of R bar must be equal to the Casimir operator of H on V, because this term here, sum over omega k times R bar of omega k, is what appears in the definition of Q of R. Yeah, so that's that. Okay, so we understand this standard Laplacian. Now we want to understand the Lichnerowicz Laplacian. So the idea is to analyze the difference. We can write down the difference because we know what the difference between the connections is. And in fact, we get this formula. And if we assume that we are on symmetric tensors of any valence, so we are on SP of M, then these Q of R and Q of R bar also behave nicely with each other. So they somehow vanish, or they don't vanish, but they get meshed together in this zero order part, A star A. So this works only on symmetric tensors for some reason. On other tensors, the formula is a bit more ugly. So the question is now, what do we do with these difference terms? So we have this first order term A star bar nabla and this zero order term A star A. How do we represent them? What do we do with them? Yeah, and this is where more representation theory comes in. So if we consider this A star A and some tensor bundle again means, or take this specific tensor bundle, so a tensor power of the tangent bundle. We can write down this formula. If we include this tensor power of M into this tensor power of the Lie algebra G, then we can write A star A in terms of Casimir operators. Okay, let me briefly go over the occurring terms. So just the last term here, we have this Casimir operator of H on M. This is actually the least worrying thing, because if we're interested in the stability of Einstein metrics, so if we assume G to be Einstein, then this must be a constant multiple of the identity. This is a classic result. In this case, this multiple is also given by 2 times E minus 1 over 2. Okay, this is pretty cool. So the second, so if we extend it as a derivation to P tensors, we just take this multiplied by P. So the second part, well, this is the Casimir operator of H on the H module M tensor power P. So if we want to calculate its spectrum, we just decompose this tensor power into its irreducible parts and use Freudenthal's formula. Not very difficult if you know how to do it, but this first term is a bit more involved, because this G Casimir does, of course, not generally preserve our tensor power of M. So this projected Casimir operator is difficult to compute. What we can do is we can give some bounds. Yeah, because of the time, let me maybe skip this example here. But yeah, let me talk about the first order term. Okay, there's a typo here. It should be A star. It should be A star bar nabla. Okay, so this A star bar, so this A star A was acting just fiber-wise. This A star bar nabla does not act fiber-wise. It's a differential operator. It acts on these sections of the tensor bundle, or equivalently on these equivariant functions. If we think of these, if we look at this space, C infinity of G and so on, if we forget the H invariance, if we embed the image into the tensor power of G, then we get another G module where G acts with the left regular representation on the first factor and with some power of the adjoint action on the second factor. And we can utilize this as before. We can write a formula that's even more involved. I'm not going to explain the individual terms here, but it just so you see that it's possible. And what we get in the end is an exact formula for the Lichnerowicz Laplacian on symmetric tensors, if we assume G to be Einstein. So this is basically what it boils down to if we put everything together. Now, the issue in computing the spectrum, as Koiso did in the 80s, is that these two terms here are a bit troublesome. They are hard to compute exactly. In some cases, so I do not know how to do this in general, but what we can do is give some bounds. So we write down two estimates. First of all, I mean, we want to settle the stability. So it would be good to have a nice lower estimate for the Lichnerowicz Laplacian. And there is this crude estimate. The formula looks a bit ugly, and the estimate is also not very sharp. But it does have the advantage that the only things that occur in here are the Casimir constant of this gamma and some bounds on this A star A term. So it's very efficient to compute. We only need to look at this A star A term once, bounded from below and above, and then compute this Casimir constant for the Fourier mode gamma, and then we already have a lower bound for the Lichnerowicz Laplacian. So this is great for implementation. But yeah, it's not very sharp. It's very, very crude. We can refine this. We can use this formula that we just developed and write down an estimate like this. So this is for this, and to compute this, we have to look what the Casimir operator does on suitable subspaces. So this, I mean, the formula looks a bit ugly, but it's written like this because it is a very, it's good to be implemented. We just have to, I mean, the projections, as you may note, do not appear here anymore. Okay, so yeah, it's hard. It's costly to compute. It's possible, but it's very much better. So okay, what is the strategy now for testing the stability of some normal homogeneous space? So first, yeah, we take this or traceless tensors as testless symmetric two tensors as a tensor bundle. We find some bounds for this A star A. Then we apply this crude estimate to narrow down our Fourier modes to some finite set. So we find this cutoff constant such that if this Casimir operator, this Casimir constant gets too large, then this Lichnerowicz Laplacian also gets sufficient, gets large enough, larger than 2e. So recall, so look at this, maybe look at this formula here. So in the crude estimate, if we make this Casimir constant sufficiently large, then also this Lichnerowicz Laplacian will get larger and larger on gamma. Okay, so if we do that, we can do that algorithmically. Then we get a finite set of Fourier modes of highest weights of G that remain, and on these one we individually apply this refined estimate. And this narrows down the set of potential instabilities even further. With a potential instability, I mean a Fourier mode that might contain tensors that are unstable or destabilizing. We should also incorporate this divergence. We have this dimension formula earlier, and this can also be done. We just have to compute the dimension of some Hom spaces. So the result after all this, if we apply this algorithm or this sketch of an algorithm to a normal homogeneous space, is that either we get a stability result, hooray, or we are left with a handful, so usually like 2 or 3 Fourier modes, which may still harbor potential instabilities, but where we don't know what the Lichnerowicz Laplacian does exactly. So this can be implemented and has been implemented in SageMath. It's a nice computer algebra system, and it has an interface to the software package Lie, which is useful for Lie theoretic computations. Okay, let me, this is, I think this, my time is nearing an end, but my slides are too, so let me show you some results. So there are these nice 2 classifications. So first of all, the classification by Wolf of isotropically irreducible spaces that are not symmetric, and the classification by Wang and Ziller of isotropically reducible spaces where G is simple and which carry a normal Einstein metric. And there is a similar question, or maybe a more restricted sense of stability, where we're only looking at G invariant variations of the metric. So this is called G stability, and this has been analyzed on these Wang-Ziller spaces by Emilio Jorge and Cynthia Will. In total, there are 19 infinite families to consider and 35 exceptions. And if we do this, if we apply our implemented algorithm to these spaces, we actually obtain many new stability results. So here are some examples. I might want to say that up to recently, the only known examples of a stable Einstein metric of positive scalar curvature was these symmetric spaces by Koiso. But this is not the case anymore. So there are actually a lot more. Still homogeneous, but yeah, so these are the ones from families, and there are also many exceptions, which would be too long to list. Yeah, and this is my talk. And if you like, I can show you briefly this program in action I have prepared. I hope you can see this. So, so we take, so let me explain what happens here. We take C7, so this is SP7, C3, so SP3, and the branching is also implemented here. And if we do that, then this program does precisely what I described. So it works out bounds on A star A, and then it scans each of the Fourier modes that may harbor potential instabilities. And it turns out, it turns out that on these Fourier modes here, so this is expressed in the basis of fundamental weights. So on these here, we have stability, and there's only one Fourier mode, this 1E2, where the Lichnerowicz Laplacian is bounded below by 1/5, which is not enough for stability. So we might have some unstable reactants here, but we don't know it yet. Let me show you a stable example, or it should be stable. So we have this E7, G2, C3. So this is one of the exceptions. If we do this, so this computes it in real time, then it turns out, after scanning the relevant Fourier modes, that the Lichnerowicz Laplacian is in fact greater than 2 times the Einstein constant. So this space is stable. Yeah, and we can do the same for all the other spaces in our list. So that's it, and thanks for your attention.
Thank you for a really, really nice talk. Are there any questions?
Paul?
Yes. Hi.
Can your algorithm work also with the trivial representation?
With trivial representation, you mean like the Laplacian on functions?
Yeah, no. I mean the Fourier mode associated.
Oh yeah, of course. Right. But if we take this Fourier mode, so these spaces that I chose here were isotropy irreducible, which means that there are no invariants. So there is only one invariant metric up to homotheity. So there are no invariant variations, no invariant tt-tensors. But of course, we can also apply this to other isotropy reducible spaces, and there it also it also works on this trivial Fourier mode of invariant tt-tensor. It does. The estimate might not be the best, though. That's kind of the problem. I know that there were better approaches to this.
I have another question. Have you found infinitely many examples of stable non-symmetric Einstein manifolds, or we are still on finitely many?
Yeah, no. So this computation only works on a case-to-case basis. So we can only check finitely many spaces. After that, our computation capacity runs out. But it is helpful for making conjectures. So there are some families where I would say, well, where it looks like they stabilize. So the conjecture would be that they are eventually stable. And there are some families where the estimates on some Fourier modes get better and better, but there are like 1 or 2 remaining Fourier modes which just never go over this critical eigenvalue. So the conjecture would be that these families the members of these families are always unstable. But to verify these, one would need to maybe, try some other approach, or try to do this algorithm by hand for a general parameter.
How difficult it is to do it by hand for arbitrary?
Okay, I did not. So I tried it by hand for some examples. This actually works. But for these general families, I mean, you would need to know exactly how these representations decompose and what the Casimir eigenvalues are. And I think it's probably possible, but it might take some effort.
But the
So I think
difficulties
it's
are
within reach. Yeah. Sorry.
But the difficulties are theoretical, right? Are from lithium.
Yes, I think so. Yeah.
Okay, great talk. Many thanks.
Thank you too.
There's a question in the chat, just a small question of the notation sub tt, on the tensor. I mean, on the subspace for divergence. For divergence and trace free, but just kind of wondering why tt was the question in the chat.
Why tt? Okay, that's a good question. This name tt-tensors, it comes from physics. So tt stands for, I did not explain that, stands for trace free, which is obviously what's happening, and transverse. So this transverse is a way to express means just divergence free, but transverse really means that we have this divergence free net as a gauge condition. So I talked earlier about this diffeomorphisms. If we apply it to the metric, we get this diffeomorphism orbit, along which the Einstein-Hilbert action is constant. So we really want to mod out this, and infinitesimally, this is achieved by this gauge condition of requiring our tensor to be divergence free. So this is why it's called transverse, because it's transverse to this diffeomorphism orbit.
Ah, great. Are there other questions? With that, thank you again. It's really a beautiful talk. Really interesting.
Thank you.
Results.
Okay, so let me now look at